We have a small ball P of mass 0.8 kilograms held at rest on a smooth horizontal table. So that means that there is no friction. And it's attached to a rope. The rope passes over the pulley, is attached to this mass Q. That has a mass of 0.6 kilograms. So let's just draw that weight force onto our diagram. That'll be 0.6 G. And as usual, we have tension, tension. We're told the ball is released from rest, so we know that U is equal to 0, the initial speed. The rope is taut to begin with. We have some distances as well. We're given the 1.5 meter that P is from the pulley, and then we're also given the 0.4 meters that Q is from the ground. It says Q hits the floor, and it does not rebound. And then we have our modeling assumptions here. So they're fairly standard stuff. Balls are modeled as particles, the rope is light, inextensible, the pulley is small and smooth. So then for part A, it says show that the acceleration of Q as it falls is 4.2. So let's get our equations of motion for both P and for Q. So for P, it's quite straightforward. For P, there's only one force acting in the horizontal direction. There is no friction, as it's a smooth horizontal table. And if there's no friction, then that means that T towards the right is the resultant force, and that will then be equal to m, its mass, times A. So I'll call that equation 1. And for Q, we have, it's going to be accelerating downwards. So then the force of 0.6 G must be bigger than the tension force. And if that's the case, the resultant force will then be 0.6 G minus T. That will be the overall downwards force. And that will be equal to ma, its mass times its acceleration. And the easiest way to solve these two simultaneously, well, you can sub in, to be fair. I like to just add them. I'm going to add them, and I end up with the T's cancelling. I get 0.6 G is then equal to 1.4 A. Rearrange that. A is then 0.6 G divided by 1.4. And when you type this into a calculator, you will end up getting 4.2 meters per second squared exactly. So on to part B. So part B is asking us to find the time taken by P to hit the pulley from the instant when it is released. So P travels a total distance of 1.5 meters to the pulley. But before it reaches the pulley, Q will hit the ground. Q will travel a distance of 0.4 meters. So what will happen is, as the system accelerates, so as P accelerates to the right, as Q accelerates downwards, eventually Q will hit the ground, and that's after it's traveled a distance of 0.4 meters. Whatever speed that Q had when it hit the ground will be the same speed that P has at that instant in time. The string then goes slack. As you can imagine, Q is no longer falling, P still has some momentum, so it continues to move towards the right, but the tension in the string will then become 0. As you no longer have Q falling and applying tension or creating tension in the string, because the surface is smooth, that would mean that whatever speed that P has as Q hits the floor, that will be the speed that it continues to move at for the remainder of the distance before it hits the pulley. So how we should approach this question is to break it up into two stages. Stage 1 is when Q hits the floor, or as Q travels towards the floor and then hits it. And then stage 2 is after that. So after Q has hit the floor, and then P moves with a constant speed towards the pulley. So let's start with stage 1. So for stage 1, we know that the distance traveled by Q is 0.4. We know the initial speed is 0. The initial speed is 0, as it says in the question that P is held at rest, and then it's released. The final speed we are interested in, the final speed we do want to work out, because this will be the initial speed for stage 2, and this will be the speed just before Q hits the ground. The acceleration would be the same as before, 4.2, and then the time we don't have, but we're trying to work that out. We want to work out the time it takes for P to hit the pulley. So there's two stages. We need to work out the time for the first stage and the time for the second stage, and then add the two things up. So now we use our Suvat equations. So I'm going to start by working out time. We have S, U, A, and we want to work out T. So the equation that relates those is S equals UT plus half AT squared. u is 0, so the equation then just becomes s equals a half at squared. Rearrange for t, we end up with t is equal to 2s, so bring the 2 up, bring the a underneath, and then square root, that is time. Put in our numbers, 2 times 0.4 all over a, and this ends up being 0.4364 seconds. And now we work out what v is, the final speed for stage 1. We can use a few equations. We can use v is equal to u plus at, or v squared is u squared plus 2as. I'm going to use v squared is u squared plus 2as. I think that's a good habit to not use your previous answers, if possible, to work out future ones for these kinds of SUVAT questions, just in case you made a mistake with this time, though in this case the time is correct. U is 0 again, so v squared is 2as. V is then root 2as, or the square root of 2 times 4.2 times 0.4, and this ends up being 1.833. Okay, so we have the final speed for stage 1. We have the time for stage 1. I'm just going to underline these so we can see them easily when we come back to them later. So now for stage 2, so let's just go over what stage 2 is again. Stage 2 is when the ball has hit the ground, so Q has hit the ground, and P still has some momentum, it still has some velocity. The string goes slack because Q is no longer falling, it's no longer pulling on the string because it's hit the ground. But then because of P's momentum, it will continue to move. It will continue to move towards the right with the same speed that it had at the end of stage 1 until it hits the pulley. So the distance, let's start with that. If we look at the diagram, the total distance is 1.5 meters, but it's already moved 0.4 meters in stage 1. So the remaining distance would be, well, 1.5 minus 0.4, which would be 1.1 meter. The initial speed will be the final speed of stage 1, which is 1.833. The acceleration, okay, so now, because the string goes slack, there is no tension, remember, so that means that the acceleration would be 0. The final speed, well, if the acceleration is 0, the speed is not changing, so the final speed will also be 1.833. And the time is what we're trying to work out. So whenever acceleration is 0, all of the SUVAT equations just boil down to 2. One of them would be the initial speed is the final speed, which should make sense. And the other equation is that speed is equal to distance over time. So whenever this is the case, and you'll see this in projectiles in year 2 as well, whenever the acceleration is 0, the only equation that you use is speed is equal to distance over time. So then speed is equal to distance over time. The time is then the distance over the speed. Divide the two things. We end up with 0.600 seconds. So this is the time for stage 2. This is the time for stage 1. And now we just add the two things up and we get our final answer. So for part B, final answer 0.4364 plus 0.600, and this ends up being 1.04 seconds. And then finally for part C, state one limitation of the model that will affect the accuracy of your answer to part A. This is a bit of a strange question. The only things that we can consider are the things that are specifically listed as our modeling assumptions. So these things here. The balls are modeled as particles, the rope is light and inextensible, and the pulley is small and smooth. All of these are our assumptions. So then for part C, what we need to do is basically say that these things don't have to be true. So the balls are not particles in reality, they have finite dimensions. The rope is not light, it has mass. The rope is not inextensible, it can stretch. The pulley is not small, it has dimensions. The pulley is not smooth, it has friction. So any of those things we can mention and get a mark. What we can't mention, and this is specified in the mark scheme, are other things which aren't specifically mentioned as modeling assumptions. So things like the fact that there would in reality be friction on this table. It states in the question that it's a smooth horizontal table, so the question is saying that this is actually a smooth table. That wouldn't in reality be true, so I don't see why this wouldn't be a modeling assumption, but there you go. So just bear in mind to consider only the things that are listed as modeling assumptions. Air resistance as well, that would also in reality act on this particle unless it were in a vacuum, but that would not get us a mark in this case.